Thank you very much for the introduction, and also thank you very much for the organizer to invite me for this nice conference. I'm actually really pure mathematician, and I didn't really understand what the physicists talked yesterday, something like that. So I'm very sorry, but I try to explain how to justify the physical argument by mathematics. So, sorry, I forgot. So this is joint work. So I often collaborate with French people. So joint work with Andrew from École Polytechnique and Arnaud Dubuche from Rennes. And the first, what I want to do, so this is trivial things for you, but our motivation is from Bose-Einstein condensation. We are interested in the model of quantum fluid. And you know the gross-Pythagorean equation is derived from mean field limit, and modeling is from Hamiltonian like this, n-body particles. And the interaction is, we consider the two-body interaction with delta potential. And we have, so by mean field Hartree approximation, we have this gross-Pythagorean equation. That's, in mathematics, we have large general theory for nonlinear Schrödinger equations. And it is a part of the non-statistical theory of nonlinear Schrödinger equations. And so we put, so since we are interested in the model of Bose-Einstein condensation, we put potential V of x here to trap the trapping potential. And but today, I wanted to talk about gross-Pythagorean equation. This is in the case of absolute zero temperature, but we wanted to analyze mathematically the stochastic gross-Pythagorean equation. We learned from these references in physics, Jean Stuf, Gardiner Davis, or some other people, like Weyler, I didn't write. But we can model the temperature effect in the condensation, adding the dissipation, and the noise, Langemann noise here. The noise is white in x, or white in space and time. Both is in time, both white. But the physicists, so in these articles, they assume always, they project PC here. PC is a projection to the lowest energy mode to derive the model equation and use this white noise in space and time. And our motivation is, so first I read this sentence. Our motivation is rigorously in mathematics leads the not putting the projection. We can treat in mathematics the infinite dimension model, and also make sense. So if we consider the stochastic PDEs, stochastic gross-Pythagorean equation, if we put the noise and dissipation, this is no more some classical things. We have to consider as the equation from statistical physics. And we are interested in the stationary states in the equation, moreover. And this is energy for the equation. Energy is from Hamiltonian. And if the temperature is completely zero, absolute zero, we consider always, also in mathematics, we consider always ground state or stationary state or vortices and like that as a stationary state for PDEs. But now, today, we want to analyze the understand, gives measure, gives equilibrium for the equation, the stochastic, with the stochastic term. But first, so formally we can write, so the physicists write, normally the given measure is like rho t here, I wrote that, exponential to the power minus Hamiltonian, and deep psi. But the deep psi is a function that belong to infinite dimensional function space, and for me, so we should make sense in mathematics. This gives equilibrium. So we will do in mathematics. And so we write the stochastic GP in infinite dimensional case. So we will not put the projection to the equation. We will study the all energy states like that. And also we write the equation in dimensionless form. Just we pick the important parameter to do analysis in mathematics. So the setting is like that. The setting is like that. We translate the physical terminology to the mathematics. And first, we define probability space. Omega. I write omega because in the equation there is a random element by the white time or white noise. And this is white noise, dW. And the dissipation term is gamma here. Gamma is positive. This is coefficient for dissipation. And the dissipation term is balanced with the noise with square root 2 gamma. And we assume, so we use the potential V of x is x squared. And nu is chemical potential. That corresponds to chemical potential. And we consider, so in mathematics, we always consider all signs, so all signs, plus minus 1 signs for the nonlinear interaction. But my interest in defocusing case, defocusing case is usually physicists use such case. So I recall that the linear part of this equation, linear part is Laplacian minus x squared. Here, this is linear part. Sorry, if I put nu, for the simplicity, nu is equal to 0. In such a case, the linear part is Laplacian minus x squared. And this operator is very known as harmonic minus Laplacian plus x squared. Has the discrete eigenvalues denoted by lambda k square. Lambda k square is explicitly can be explicitly written by in k, and hk. This is eigenfunction for this operator. This is Ionut function. You know very well. And we define dw, the noise in white in time space. And how to define this noise in mathematics? We call this cylindrical Wiener process, or L2. L2 is, sorry. L2 is just, so on RD square integrable functions. I noted by L2. And so that doesn't have any meaning, in fact, L2. But the WTX we define like this infinite series of beta k and hk. Beta k is the C-valued independent Brownian motions, and hk is Ionut functions. So in this form, if we describe WTX, we can have E is a measure to probability space PD concerning P. That means the expectation in the probability space, and E if we calculate E of W, Tx, Ws, Y, and we will have this element for the time because that's from, so Tx, Sy is beta kt, beta ks, hkx, hk, sorry, y. And this is the just Brownian motion, the correlation Brownian motion. So if you derive by time here, if you derive, so if you differentiate in time here, you will have the delta S minus T here from here. And for the delta correlation, to see the delta correlation in space, if you look at this hkx, hky infinite series, you will have in the weak form of this quantity, so testing by a smooth function phi, you can calculate this quantity as, in fact, equivalent to delta x minus y phi. So the right-hand side equal left-hand side. So in fact, this quantity is delta x minus y. So we define in mathematics this infinite series as white noise in space and in time too. So we treat directly this WTX. Actually, this is not the first time to treat theoretic PDEs. There are many cases already many studies already. For example, concerning the Gibbs measure, that is started by 16th by Simon Leib from the point of view of constructive quantum field theory. And also, Gibbs measure is frequently always used for the analysis of nonlinear dispersive equations. This is a Hamiltonian system. So Hamiltonian systems have, as an invariant quantity, the Gibbs measure. So we can use as an invariant quantity to globalize the solution in the theory of dispersive equations, the Hamiltonian system. That's what's used by, for example, Lvovitz first, and Burgan. Burgan is a famous mathematician. And he contributed with this theory many things in the nonlinear dispersive equations. Also, that continues the use of Gibbs measure in the theory of PDEs by Nicolas Birk, Patrick Gia, Laurent Thomas, Nicolas Best, that this is a mathematicians, all mathematicians. And also, the Hamiltonian case, I mean that this case is nonlinear dispersive equations without dissipation and noise. This is just deterministic Schrödinger equation, I mean. But if you add white noise here, a stochastic case, for example, for the BEC model, Karen Flores-Lvovitz also studied, but not white noise, regular correlation case. Also me with Devoir de Vuche in this talk. Also 5-4 model. 5-4 model is dissipation with dissipation, the heat equation, but without potential, normally on the torus. And this is done. This was done d'après Vuche. These people here, Weber, Alberi, Yoksuka, Gubinelli, Hofmanova. But these studies for 5-4 case actually have been very open problem. Have been problem as very difficult problem. But 2014, Martin Heiller invented the theory of regulated structure. He gained Fields medals at that time to solve the FIFO model in 3D equation, 3D SPD. And thus, the development accelerates now in the stochastic PDE theories. First, I will go back to our equation with linear operator here, minus Laplacian plus x square. And if we consider, so the difficulty in mathematics is always if the dimension is increasing the problem to make sense to the, give us things to the equation, it is very difficult if we put the noise in space. So we start with the dimension 1. The dimension 1 is comparably easy, not difficult. And we have this Hamiltonian. And I explain, so this is very not a difficult case, so I give you the idea how to analyze in mathematics. So to give a sense, to give this measure in one-dimensional case, just we formally write the Hamiltonian here. And we give a sense first this term with using the decomposition development with the eigenfunctions, limit functions. But for the moment, we cut until n, for example, until large n. Just we consider the finite dimensional case. If we consider finite dimensional case, this stuff gives just finite dimensional gives a Gaussian measure. Here is Gaussian measure in finite dimensional case. We know well to analyze how to analyze. So and we add this nonlinear term. And so in mathematics, we call it the limit. The limit here as large n goes to infinity, that gives a measure. If the limit exists, if the limit can be well defined, we call this limit gives a measure. So we don't know a priori if we can write this explicit form because this is a limit. But in one-dimensional case, we can conclude that this is a Gibbs measure. So in fact, this is a Gibbs measure, and in this form, we can justify. But we can justify the limit, but the sense of limit is important in mathematics. So in which topology, so the limit, what is the sense of this limit? It is the interest of mathematicians. So to know which topology, in which norm, in which topology the limit exists or not, we investigate first so first the equation was nonlinear. So the psi so original equation we wanted to treat is with nonlinear term, cubic nonlinear term here, and the linear part, including the noise. This is a linear Langevin equation here, this one. And we know that, in fact, the Gauss here, this is Gibbs measure, and this is Gauss corresponding to Gauss measure. Gauss measure has same regularity as the solution of this linear stochastic equation. We know that. So we investigate the regularity of this solution of this linear part of Gross-Pitarski equation. And if we calculate, we estimate all things in this equation, in the element of this equation, this solution, using the form of noise, infinitely series of beta k and hk. We insert this form, we can in fact easily estimate the which topology where Z lives in. And the conclusion we had is Z is in LP almost surely. Almost surely, that means the probability 1 that lives in LP space, but P is larger than 2. P is larger than 2. That means not Hilbert space, but we generalize the space rather than Hilbert space, like P here, P moment. If we look at the P moment, we succeed to give a sense to the linear part of stochastic Gross-Pitarski equation. And then, since I told you that the Gauss, the Gibbs measure is written with exponential minus nonlinear Hamiltonian, nonlinear part of Hamiltonian, multiplied by Gaussian measure, the linear part. So if I can see that is in LP, P is larger than 2, that means that support of Gaussian measure is in LP, P is larger than 2. And also, that means Gibbs measure is supported on LP, P is larger than 2. So in such a way, we see that the first support of Gibbs measure, on which function spaces we know, we can see the support of given measure. And like this. We will advance like this. For a moment, this is the result. For one-dimensional case, it's all the result in 2018. But using so knowing the support, the given measure, we use this topology. We apply this topology to all equations, so to treat the equation, and the equidistance of solution for stochastic Gross-Pitarski equation we can do in that space. So on the support of this measure, we can construct the solution for the stochastic Gross-Pitarski equation globally in time first. And once we can define the solution for the stochastic Gross-Pitarski equation, we can consider the law in time, law of the solution, which is described by this quantity. Psi is the solution. Psi is the solution, and we take expectation with a test function like this. So this is the definition of the law of solution, and the law of solution. Finally, we can also show that converge to the Gibbs measure. Gibbs measure which is defined on LP, P is larger than 2 here. So we can justify by mathematics the convergence to equidistance of Gibbs measure, equidistance of solution, also the convergence of the system to the Gibbs measure to t goes to infinity. Also the rate of convergence to the Gibbs measure is exponential minus gamma t. Explicitly we can write. I didn't explain details for the mathematicians because maybe it's complicated. The difference of first theorem and third theorem. This seems very similar for the physicists, but just I add a remark. This is just almost every year initial data, global equidistance. But this one is for any for any initial data, we have a unique global solution. So there's a little bit gap. There is a little bit gap in mathematics. But anyway, we can have the global in time, unique solution for the stochastic GPE in LP, p is larger than 2, strictly larger than 2. Sorry, for the, I forgot the p is larger than 3. And in mathematics, we have to treat nonlinearity here. So this is cubic, so it's the distribution on the p again comes from the nonlinearity. So in total, in fact, we have to assume P space of LP space should be larger than equal to 3. But for one-dimensional case, I think it is completely solved by mathematics for stochastic GP equation. But normally, we are interested in 2D and 3D, I know. So I wanted to do 2D and 3D. But for the moment, just a part of 2D, we can do something. And for the two-dimensional case, so I go back to the argument to know the support of Gibbs measure. What is the argument to define, so to determine the topology where we can consider the solution of this nonlinear stochastic PDE? We have to investigate the linear part, linear Langevin equation, linear part of Gross-Peterski, and the solution, the regularity of solution that gives the support, the space of support of Gaussian measure, the linear part of Gibbs measure. So if we consider first a linear stationary solution, linear solution of the Gross-Peterski equation with stochastic term, now in two-dimensional case, we have this regularity. I think that this is really quite optimal, this regularity. We cannot improve, I think. But the problem in 2D is, in fact, W minus S square. I wrote this, minus is also, please remark that minus S is positive here. Minus S is positive here. And minus S, what is minus here, index here? It describes the derivative. Which time we can derivative. We can do the derivation. And Q is just integrability like this thing. So the problem is about this regularity, about the differentiation. The negative time of derivative we can do, but not positive time. So this is not a really normal function space, this distribution sense. And also we know that if we wanted to, so this is a solution of linear equation. But if we wanted to treat, again, adding the nonlinear cubic term, we have to give a meaning to nonlinearity here. And we know already that if the solution is in the negative index of the derivative, we cannot define the multiplication of that function with negative regularity in mathematics. So we have to do something to give a meaning to the equation. So here, already we know one method. We call that Doppler-Division trick here. He is my collaborator, so he knows well. And first, we decompose the equation of the solution of nonlinear stochastic equation here to U plus Z I wrote. Z is that part with negative derivative, negative regularity here. Derivative. Concerning the derivative, this is a bad part. So Z plus U, we expect that U is more regular. So we decompose the two parts, and we analyze separately. So Z is too bad because of the noise. The noise regularity is too bad already in two-dimensional case. Because of that, Z has negative regularity. So if we subtract the bad part, usually or U, so subtract the bad part, the remaining part has good regularity normally. So if you write U, the equation for U in this form, we know that this is just PD, not a stochastic PD. It is just PD, and we can treat the equation of U as standard deterministic PD. Just a random element is in here, the nonlinearity. But as I told you, here, if you develop the cubic nonlinearity, like here, there is a multiplication term by the bad regularity Z, cubic, and twice, the power of twice, blah, blah, blah. So we have to do something about those terms, which does not have meaning. So how to do? We use renormalization. This is the idea, I think, from the, なんていうんだっけ。バノリオシロンってなんだっけ。So just the weak product we use. We define the weak product using the Ionut polynomials. And we replace. So the problem is this part, for example, cubic. So we replace. So subtracting the bad regularity part, we define weak product dot dot like this, and we replace the real cubic nonlinearity by dot dot power 3. And in that sense, we subtract the bad part from the bad cubic term, and we can give a sense, in fact, if we do, for the nonlinearity. And the regularity, so the topology on the support, the relative for the support of given measure also we can know. And first we can prove, I think many things, but we can prove just a theorem I show. It's very complicated as a statement, but just if we consider, so we decompose in 2D, we decompose the Psi as U plus bad part linear part of stochastic equation, and the term which is remaining in the solution can be treated by the standard PD argument if we renormalize the bad part from cubic nonlinearity. We can say that first, the locally condensate, so locally in time, we can justify the stochastic GPE using the renormalization technique for the nonlinearity. The U here, we can solve the equation for U in this space topology. So mainly, so U is the solution of nonlinear PDE, but the regularity is W minus SQ, just minus SQ. S is positive. So otherwise, it is in the negative regularity, but we can solve even if we decompose like this and we subtract the bad part from the nonlinearity with renormalization. Also, we are interested in the globalization of the local in-time solution. We can do it, actually. We can do the, how to say, the energy method, just to energy method, very complicated energy method, but simply I tell you our result. Yes, there exists a unique global solution U in the same space, in fact, as local existence. And otherwise, U is continue in time and space regulated W minus SQ. And finally, about the Gibbs measure in two-dimensional case. So we know the solution for the stochastic GPE live in W minus SQ. The W minus SQ, the regularity is a little bit negative. And Q is larger than 2. The integrability is larger than 2 always. Also, if we want to give meaning to the Gibbs measure, we write again in this form. And give a sense first the Gaussian measure part, linear part. The Gaussian measure part is the same regularity as the support of the Gaussian part, the same regularity as Z here. The Z is always W minus SQ, and minus S here, and S is positive. So this is always negative regularity. It's rarely problem. But as we did for the equation, we do again the renormalization. We use renormalization technique for the Gibbs measure too. That means the nonlinear part here. To define this nonlinear part, since we cannot consider the support for the Gaussian part here. I want to say, if we wanted to give a sense for this nonlinear part, this is the L4 norm here. L4, you know L4 norm. So this is psi 4 to the power 4 integral on L2, R2. So we cannot give a sense directly for this quantity because psi is in W minus S, so minus S is negative. So, sorry. So for if I say L4, for example, LQ, anything, Q, that means W0Q. And the solution live in minus regularity here. We cannot improve the regularity up beyond the 0. So beyond to the 0. So we cannot anyway, we cannot give a sense to that quantity. So we renormalize this nonlinear. So not cubic, in this case, fourth term, nonlinear fourth term. We subtract the bad part from this nonlinear term. And we cut like that. We use a projection to the finite dimensional case, and this is a subtraction of the bad part. So this is the projection to n finite dimensional space, and in this equation we subtract already in finite dimensional case. We subtract the bad part we can expect. Here, C. Here, C. Here, this corresponds to the infinite dimensional case, the bad part, the bad regularity part in this fourth nonlinearity. And if we do this step, we can in fact justify the limit. The limit n goes to infinity exists. So in the mathematical terminology, we say that the finite dimensional cut with cut n is tight. The measure is tight. In this space, W minus SQ, that means that the measure is a measure converted to weak sense, but in measure sense, to some limit in this space, W minus SQ. So for the weak limit, so for some, so we have the limit, some low. And this measure is invariant measure, but we don't know. We don't know. Just equidistance limit we can justify, but we don't know the form of the measure. So we don't know the form of exponential minus Hamiltonian form. I don't know, but just we can see that the limit exists. So that should be gives the measure for the two-dimensional stochastic PD, stochastic group equation. Okay, so that's all our result. But if we want to go further in mathematics, for example, the property of the limit law in two-dimensional case, it is a great interest, of course. Also, three-dimensional case we have to do anyway, but it is more complicated because the regularity of noise is getting worse if dimension increase. So it is quite difficult for a moment. Okay, I stop here. Thank you very much.
So, mathematical questions or physical questions?
Thank you. I have a curiosity about the noise term. It was in the very first part of the talk. So it's about how you implement this space-time noise. And if you can comment on it, because it looks to me that from the physical point of view, it's a bit strange. Exactly like here. So if you look at the formula for W, you have basically that if you fix a slice, a time slice, you always have a certain profile, and then this profile is constant and is just modulated by beta. Am I wrong? Yes, I'm wrong. Yes, I'm wrong. Okay, no.
You got, yeah.
I got it. Thank you.
Beautiful.
So the noise here is additive. So can you consider the multiplicative noise?
Multiplicative noise?
Multiplicative. So the noise is the additive one, right? So you have this dW times precise, yes, something like this.
Yes.
So is the will the results be extended or generalized to this kind of case?
That's not my result. I think in fact, so for one-dimensional case, it's not so difficult, I think. But two-dimensional case, there is a technique by using the transformation that recently used Hendrik Weber and Arno Dubuche. And with using this technique, so the transformation have psi exponential noise, something like that. You can solve locally, or at least I think the equation. But this is in progress. This is a work in progress with students. So I know. So we can treat multiplicative noise too.
Thank you.
Thank you. I may have two quick questions. The first one, is it the same gamma which is before the noise?
Yes,
and
this is the same gamma. Should be same. And balance should be rarely this balance, gamma and square root 2 gamma.
This is the same
to
for
have
the dissipation.
The measure is invariant.
Okay, so it makes sense for the exponential convergence. And is there the same kind of result on the torus with only the Laplacian and no harmonic trap? Because it may be simpler for my point of view that an
on the torus.
Yeah, on the torus,
on
but
the
without
torus.
the. Yeah.
But if you consider on the torus, you don't need to put the potential.
Sure. But there is the same kind of result.
Yes, that's a 543. If you consider the same kind of equation without potential, this is 5-4.
5-4. Ah, okay. Ah, okay. I see. I see what you mentioned. Okay.
Other questions?
So in some of the results that you cited, like Lebowitz, Rose, Spear, and so on, there were techniques that were genuinely one-dimensional, like transfer operator methods and so on. So you did not talk at all about these kinds of methods. Do they have any bearing in what you're doing? I guess in some of the things like 2D maybe less so, but in 1D they could in principle be applied, or?
1D, yes, but I think mainly their technique is to treat focusing case, right? I remember. Focusing case, we need to cut the measure, to give a sense, and we consider only defocusing case.
Right,
so
they did not do the defocusing, as I remember, yeah. So they did not do it.
No, I didn't do. I didn't do.
Great. So, just a comment say that it's not only mathematics, but I think it's related to real models used by physicists in dealing with BEC and thermal clouds. Right, Nick? So, brings a justification from
Thank you very much for your support.
So, it's not disconnected as we like to think, physicists like to think about mathematicians to be completely disconnected from physics. It's not the case at all. Thank you very much, Reika.
Thank you very much.